So recently I've been refactoring some of my networking code for the 50th time. It's been an ongoing incremental process to get it as efficient as possible. And it's really important for my game because in my game, I want to basically be able to persist a whole lot of data for people like their entire history, and I want them to be able to traverse it backwards and forwards. And yeah, and I don't really want it to be that limited, but I also want it to be pretty powerful in terms of what it can represent. And the way that I started with it is the way everyone starts. You just start with some basic JSON data with key value pairs. And when I was first doing that, that's really convenient and whatnot, but it breaks down really quickly. And the last changes that I've done have catapulted the efficiency up yet another level, although earlier refactors that I did were probably actually more substantial in some ways. But it's like I've said, it's been an incremental process. So if I had to distill the most important optimizations down, it would probably come down to the first thing you need to do is move away from using JSON data directly. Now, if you want to be maximally efficient, you would need to use binary data, but working with binary data across the network and with multiple different programming languages and whatnot is really inconvenient because it's just an order of magnitude more complicated. You probably have to write every library yourself. But there are some little tricks that you can do that give you a lot of the power, but with a little bit of a trade-off. So the first thing is you can put binary data in JSON data if you base64 encode it. And so this is the first thing I did. So say you take an animal like a lobster that has life, attack, armor, initiative, some other stuff. You could represent that in JSON with a bunch of key values. The first optimization is to make all of those keys as short as possible because it actually contributes to the overall size of everything. And if you're repeating it over and over again, there's no benefit for it once you have the entire structure set up like programmatically. The only benefit is for a human reading it after the fact, which is not actually worth it in the long run once you release a system that is going to be utilized a lot. So the first thing you can do is just reduce the size of keys. So if you have a key that's like a super long key, you can just replace it with the letter A. This is still not good though, because it's still going to be a lot longer than if you do something different. So what you can do is you can take all of those logical numbers like health, attack, defense, whatever you want to do, and you can instead make them a singular byte if it's going to be a value between 0 and 256, or you can make it a larger number between 0 and 65,500, whatever. You can basically do that with 2 bytes and continue with more mathematical, informational, expressive power by adding more bytes to it. And then the key is after you do that, you can basically base64 encode that binary. And even though base64 is going to take your binary and increase it by about 37%, it's still going to be much smaller than basically the JSON equivalent. So that's the first huge optimization I saw, is just moving away from JSON key values and numbers being represented with a string and all things being represented with a string, like types also, and converting everything to a number and packing it into a binary representation and then base64 encoding it. Another trick you can do is move away from the key value approach altogether with JSON, because each one of those keys and each one of those values is going to have 2 commas around the key, 2 double quotes indicating it's a string for a key, and a comma. And each one of those is going to add up to 3 bytes. And if it's not actually that important and it's always the same order and it's a finite space, if you just convert it to an array and instead use specific indices within the array, it will take up less space. And so I was doing like such a weird combination because there's lots of different pieces of data in the game that are like that cascade. So you might have an entire snapshot for a long sequence of things that's made up of all these smaller components, a particular animal at a particular piece of point in time. But Yeah, so at some points I was base 64 encoding some stuff, but then putting that back inside of a JSON dictionary or a JSON array. But now I have effectively moved everything to just be very much so a rudimentary array for a JSON without any keys, and basically just three main values. One is like the main type for that data, like how you're going to interpret it. Two is the uncompressed size of it. This is necessary for Godot so that it can be decompressed. And then three is the base 64 compressed binary blob, effectively, that represents all of the data. And that's the last thing that I didn't bring up that's very important. I waited to do compression very late in my entire like network design, which I think was actually good in a lot of ways because you learn a lot about lots of different ways because you can reduce the size, the footprint of your data. Like I said, some of those tricks reduced it by a size of probably like 80 or 90% already. It's staggering. But with compression, you get even more based on your overall design. So the other aspect of the design in my game is that I was noticing effectively in my game, you capture almost every state change in the game, which is extremely expensive if you're going to do that. It has a lot of huge benefits. If you want to move backwards and forward in time, you can do it very simply, and it makes it easier to programmatically set everything up and debug as well. I also just think it's better. You can use it for statistics also if you wanted to, but the drawback of it is that now you've got all of this redundant information, even though very little is being changed from one time point to the next. So the first optimization I did with that months or maybe even like years ago was like I basically figured out what exactly what part of the entire data was going to actually be mutable during this particular part of the game. And then I was like, let me only focus on that part of the data. And then let me, whenever I want to save this data, take it in its raw form, which at that point was like a JSON snapshot, but now is just literally a string of bytes. And let me put it in a dictionary and let me associate it with a specific number. And what's important is that if you have cycles in your game where there might be actually the exact same state, when you use a dictionary, it will look in the dictionary to see if that pattern, that state pattern, already exists, and it will not have a redundant copy. This is especially important in like a battle where there might be hundreds of states and it might be effectively a draw. There's actually a cycle. Neither team can beat each other until the sudden death kicks in, and it's like a forced scaling, so one person wins or loses. But up to that point, it's just a stalemate. What would happen before is each one of those states, even though they were effectively the same, were being, excuse me, each one of those states were being stored. And so it ballooned very quickly, and it was clear to me that this was not sustainable. So I was like, how about I just use this dictionary and only add new states to it? That's great, but then that scales effectively with the size of each individual state that you have, and it also scales with how quickly, how frequently you're actually capturing changes in the data. And if that happens a lot, like you would expect it to, like it can happen hundreds of times potentially in a single battle or something, that starts to add up very quickly again. And the interesting thing though is when you use compression, like a compression algorithm on the binary data, it doesn't matter that there's repetitions and redundancy because the compression itself takes care of that. And that's so important because now effectively you've compressed the data before you write it to the database, and you decompress the data after you've transmitted it over the network. So you've effectively completely reduced the main performance bottleneck of the data, and now it's just on your computer, your like local runtimes, which can handle these slightly larger pieces of data. And I don't know, I'm definitely just rambling here, but this is something I do actually have quite a bit of experience with at this point, and that's what I would say is the main takeaways is you can accomplish quite efficient systems with the flexibility of JSON, but you need to treat your entire system as being a binary blob. And then with that binary blob, you need to use compression with it. I'm just lucky that compression happens to work with the design that I made already, where there is a lot of redundancy. Other strategies it might not work as well with, but it's actually like a skill set in and of itself to convert something like JSON data to binary data. And I don't think that many people are very comfortable with it actually, which is something that I got better at as I thought more about it and started to realize the massive gains you get from doing it. But some of the easiest tricks are, and I already brought this up, but converting everything to a number that you can and to a small number. Like, it's pretty complicated and tedious to work with bits, individual bits, but it's not as bad to work with individual bytes. And like for instance, in my game, there's a bunch of different objects like animals and relics or whatever, and statuses and emblems. Every single one of those has like a logical name, like lobster or whatever, but then it has a number that corresponds to it. And when you communicate over the network and in the database, you don't ever use the name because the name is like literally 16 times the size of a single number, or even more, like 30 times the size of a number. So that's the first thing. You convert logical types to a number. And there's a name for this in machine learning. I think it's called one hot encoding, one something like that. But effectively, it's just about the conversion of things to a number. Now, the next thing is when you have a list of things, there's a couple different situations with a list. There's a list that how many things are going to be in it because it's always the same number. There's a list where everything is the same size. There's a list with things that can be variable sizes, and there can be a variable number of those things. And this is really getting into information theory and how you can encode these things in binary in a way that you can traverse through it and always interpret it the correct way. And probably the best trick for that is to use two different things. If you know the fixed size of a list of elements that you're going to encode, then you can just use a number representing how many of those that you expect. And therefore, that number can be dynamic if it's changing over time. And so if you know that every single one of these items in your game is going to be made up of three numbers, the type, the cost, and something else, whatever, and they effectively take up 3 bytes, and you know that you're going to have an inventory, and that inventory has 6 items in it, then you can just make an 18-byte thing that is interpreted with a single number at the beginning, which is like 6, and then it knows to do 3-byte chunks after that. And once it finishes with that, it can move on to the next semantic part of your entire like blob. But the other situation is when it's more complicated, like each one of your items can actually have a variable length because they're different and they have more depth and complexity. Then what you need to do is effectively have a single number before each one that says how large it is. And you can do the size, typically you do the size in bytes. And so if you know what the maximum size of all of these objects are, then you can just use that same thing that I talked about before with using a number for something like health. You can be like, all right, it's never going to be above 65,000 bytes. So I'll make it a 2-byte number here that will tell me how long the next blob will be that represents the item here. And then you just keep doing that until you're done with the items. And those are like the two main ways of, or some of the main JSON to binary things. But anyways, I thought I would just make a video about this since I was just immediately working on it. And I know it's useful to a lot of games out there, but mostly to games that are very much like mine, games that are built around a database and around having a historical persistence of data. or a bunch of different players. That's when it really pays off and makes sense to do something like this. But understanding these concepts is important to probably taking on any networking problem, because even though it might not resemble exactly the stuff I'm using here, the same concepts apply to it. It's basically more or less just about efficient, the efficient use of binary alongside the convenient flexibility of JSON. But once you get out of the JSON realm, it's even easier because it's just straight binary. But like I said, it is a lot more annoying to actually get that hooked up because you got to be rolling your own stuff a little bit more. But anyways, you guys let me know what you think about this. Ciao.